Welcome to our presentation on uncertainty-aware likelihood ratio estimation for pixel-wise out-of-distribution detection. Semantic segmentation is a key component in the perception stack of autonomous vehicles. Current methods are usually trained on a fixed set of semantic classes. However, in the real world, they might encounter unknown objects. This is exemplified in this image here, where we have a trained model which faces obstacles marked in these red boxes. However, what we see here is that this model confidently classifies these boxes as belonging to the road, which can have detrimental effects. Approaches trying to identify these unknown objects are called pixel-wise OOD detection. However, they usually face difficulties with rare classes which introduce ambiguity, and hence existing models often confuse rare known classes with truly unknown ones, leading to false detections. The goal in our paper is to make pixel-wide out-of-distribution detection uncertainty-aware and hence robust to long-tail distributions and synthetic outliers. We begin by formulating out-of-distribution detection as a statistical hypothesis test and solve this via likelihood ratio criteria. To do so, we extract dense intermediate features from a pre-trained semantic segmentation model and try to estimate this likelihood ratio here, where we have P_in being the in distribution of features and P_out the distribution corresponding to all possible features that do not belong to the in distribution classes. Now, in practice, we do not have access to this distribution, and to alleviate this, we rely on outlier exposure, where we take an additional data set from which we extract objects and paste them at random locations in the in-distribution images and treat the corresponding features as synthetic proxy features. Now, this introduces another problem, because the proxy OOD features do not necessarily correspond to the real OOD features and hence introduces a bias into our estimation problem. The key idea in our paper now is, instead of relying on generative modeling, to directly learn this likelihood ratio via a binary classifier and predicting probability distributions instead of point estimates. How this looks like is exemplified here in this example, where our in distribution and out distribution are two Gaussian distributions, each centered at these means μ0 and μ1. On this toy data, we train a binary classifier and our method. For the binary classifier, we see that it reliably distinguishes between these two cases. However, it predicts very large probabilities or high probabilities in regions where it has not seen any training data. We call this overconfident extrapolation, and this leads to potentially false detections. In contrast to this, our method predicts a probability distribution. This is shown down here in these boxes. What this means is that for each point on the real axis x, we predict a distribution over probabilities from 0 to 1. The cool thing is that by doing so, we get an additional degree of freedom and enable the model to express uncertainty through the shape of the distribution. As we can see here, in this low density region, our model approximates a uniform distribution, indicating maximum uncertainty, because it does not have seen a lot of training data. Now, as we move towards regions with high training density, what we observe is that our distribution becomes more peaked and hence more confident in the predictions, enabling our model to appropriately adjust its uncertainty. The cool thing is, when we apply this to features from a real semantic segmentation model, we find that the resulting likelihood ratio reliably detects unknown objects. For example, here in this image from before, we can see that we have a high ratio only for the unknown objects. We also evaluated our method on 5 standard benchmarks and compared it to the recent state of the art. Here we find that our method outperforms the standard classifier by a large margin, and we achieve the overall lowest false positive rate while maintaining a high average precision, indicating that we effectively alleviate false detections. If you're now interested in the details of our implementation, feel free to check our paper, and I'm looking forward to meeting you in the poster session. Thank you for your attention.